Ladies and gentlemen, good afternoon from Greece, from Hellenic Mediterranean University and the Athena European University. We are very happy to continue with one more, the last one for this month, Athena Talk. Within the Athena Talks, we make our best in order to attract and invite distinguished scientists that they are visiting our university, and not only. So we are very happy to host today with us Professor Ricardo Santamaria. But since Ricardo has been introduced, and I would like to thank very much Professor Dimitra Bernardou for this opportunity of our initiative within our university, Hellenic Mediterranean University, I will provide the floor to Professor Bernardou, Dimitra, in order to make a short introduction of the today's speaker. So Dimitra and Ricardo, thank you very much. And the floor is to Dimitra for the short introduction.
Thank you, Kostas, for the introduction for Ricardo. Ricardo has dedicated a significant portion of his research efforts to the exploration of carbon materials, leading to the development of different diverse materials, including high-density graphites, carbon fibers, carbon composites, graphenes, etc. We're honored to host Ricardo as our guest in cutting-edge materials for electrical energy storage and efficiency lab within the framework of storage research infrastructure ecosystem stories. Just to let you know what storage is about, storage is dedicated to advancing technological frontiers in energy storage, offering access to state-of-the-art and service. So we're looking forward to his insightful talk regarding the carbon materials for applications on lithium-ion batteries, supercapacitors, etc. So, Ricardo.
Okay. Then I can start with sharing the presentation. Let me share this one. Let me. Okay, then I want to first of all I want to thank Konstantinos for inviting me to participate in this talk, and especially I want to thank Dimitra Bernardou for having me here for 3 months. It's a great opportunity for me. I'm really enjoying the island, and also it's a pleasure to share the work every day with Dimitra and her group. And then we are learning together many things, and I think we can continue in the future with our cooperation. Then I'm going to talk today about carbon materials for electrochemical energy storage and generation. Indeed, energy storage principally, and it's quite a complex subject. I have only 40-45 minutes to talk, then I will be very brief, and I hope you can follow the presentation. First of all, I want to introduce my institution, which is the Spanish Council for Scientific Research. It's called CSIC. I hope you can follow in here. It's the largest public research institution in Spain. It's around 15,000 people involved in science in our institution. And as you can see in the map, there are quite a number, nearly 100 different institutes all around the country, most of them in Madrid, in Barcelona, but there are a few all around the country, working on different topics, any kind of mathematics, physics, chemistry, medicine, food, also social science. We are working in different topics. And as you can see, I'm coming from Asturias, this little corner of Spain. It's not a very popular place, very few people know Asturias. I'm coming from the Institute of Science and Technology of Carbon. We are mainly involved on carbon applications for different topics. The Institute has now nearly more than 75 years old, has been in place for many, many years running. And then I'm going to start now with the presentations. talking about energy is always of interest because for our society, energy is essential. Then when we talk about society, energy, please, we involve all the society, we involve scientists, we involve politicians, then the situation is always a bit complex. Then I'm going to talk about, very briefly in the introduction, about the change in some paradigms we have to face in the future. We are talking about renewable energy and energy storage. We are going to talk about carbon materials, why carbon materials are related to energy, and what are carbon materials, what is very unknown for many people. And within the energy storage devices, we are going to talk very briefly about lithium-ion batteries, supercapacitors, and redox flow batteries. All these electrochemical systems have some kind of carbon material inside of the battery or supercapacitor. And I want to show you how different materials are used for different applications. Then going into the introduction, energy, as you know, we're using mainly fossil fuels to get the energy we need in our society. We have been using fossil fuels in a huge amount of them with a massive transformation, mainly coal, oil, and gas. And thus, in the last century, we have made a huge social development. We have many positive aspects of having this energy. We have increased our living standard, we have increased our life expectancy, we have developed health system. We can look for many positive aspects of the use of energy in our society. But of course, we have also some issues that we are not doing very well. Fossil fuels are limited, and we are running out of some of them. We have pollution in our cities, especially in our cities, in our seas, in our air. We have put a lot of stress on many ecosystems. We can see in the oceans. We can think on the forest. We can think on the Arctic, on Antarctica. But mainly, the main problem we are facing because of the massive use of fossil fuels is climate change. If you take a look to the variation of CO2 levels in the atmospheres in the last 2 centuries, you can see that in the last 100 years, the amount of CO2 has been increasing constantly, especially in the last 50 years. And this is because of the use of fossil fuels. The scientists told us that we should get 350 ppm of CO2 in the atmosphere with no problem, but in no way we should go over 400. And unfortunately, we got this level 10 years ago. And the main problem to be concerned is that we didn't stop emitting CO2. That was in 2013, we arrived to the 400, but now we continue using fossil fuels and we continue increasing this. And I think we are all aware that the climate change is already here. We see in our cities, we see in our villages how the weather patterns are changing and changing very quickly. The problem, how we produce energy. In here you have the global primary energy production in year 2000. Around 80% of all the energy we use are coming from oil, natural gas, or coal. We signed the Kyoto Protocol in 1997. We were aware that we had a problem, but I'm not going to say nothing, but very little has been done. That was the image in year 2000. That's the image in 2020. Energy is coming from coal, oil, and natural gas. We are not seriously changing how we produce energy. I think we are starting now, a little bit late, but it's better later than never. But I don't want to be very negative. For example, I'm going to see you how we have changed a little bit in Spain, how the way we produce energy. For example, you can see here in year 2000, in Spain, we were getting electricity mainly from nuclear and from coal. We have hydro, which is changeable from year to year, depending on the rains. But the scheme was very simple. Most of the electricity is coming from burning coal or using nuclear power stations. Only 20 years later, the picture is much more complex, and more than 50% of the energy we obtain are coming from renewable sources, mainly from wind, eolic. I didn't translate this one, which is a bit complex. I think you can understand. Coal, that was more than 40% in the year 2000, is only 2% in 20 years later. Coal is nearly over, and we're using mainly wind, starting with solar, and the prognostic is in less than 5 years, 6 years, we will multiply by 2 the wind production and by 5 the photovoltaic production, which is very important. Okay, and we are doing things, but very slowly. We need to go faster. Then the first thing we have to change is moving from fossil fuels to renewable production of energy production. And as you can see, some sectors are easy to decarbonize. For example, electricity production is easy to transform, but other sectors, for example, transport, is much more difficult to fully decarbonize. Here you have some images about the photovoltaic power that has been installed in the European Union in the last 20 years, approximately. Nearly nothing at the beginning of the century. Then we start building photovoltaic plants very quickly, but then we stop for some reason. You can see here in 2008, the orange one is Spain. We were very much leading the installation of these photovoltaic plants, but suddenly we stop for some reason. And we should ask our politicians the reason. Why did we stop using photovoltaics? That's very difficult to explain here. But generally speaking, all the European countries stopped because of the financial crisis. And we have nearly lost one decade, 10 years of time installing photovoltaics. And the thing is that in this period of time, the cost of photovoltaic panels was decreasing very much. When we start installing photovoltaics, they were quite expensive, but now they are very, very cheap. And you can see that now, again, we are leading the installation of photovoltaics. And in Europe, we have something like 40 gigawatts of energy, of power, every year, and increasing very quickly. To have one idea, 1 gigawatt of energy is what a power plant, a nuclear power plant, is producing, more or less, 1 gigawatt. Then we're installing 40, the equivalent to 40 nuclear power stations for year. Okay, it's not that precise, but more or less you can have one idea of what we're talking about. And photovoltaics is very important because it allows us to a new change. We have been producing energy in big central power plants, but now with photovoltaics we can move to decentralized production. We can produce in our roofs electricity for ourselves or for the grid. Okay, you can see in year 2022, last year, we have in Europe more energy installed in photovoltaics in roofs and that in the largest scale. It was 25 against 27. And in the next year, both of them are growing very quickly. And at the end of 2026, will be around 40 gigawatts of each type of generation. But that is changing the paradigm because citizens, European citizens, are becoming part of the electricity generation. We are not just consuming electricity, we are able to produce electricity. But there are very big differences between different countries. You can see here the data from 2020, the solar roofs we have in different countries in Europe. And you can see in Germany, they have 1.4 million of solar roofs working. Germany, that was Germany. Italy, 6.6 million. United Kingdom, 0.8 million. And Spain, which was leading the production of photovoltaics, only have 10,000 solar roofs. Again, we have to ask our politicians why. What are the reasons to invest so much in large-scale photovoltaics, but not in a small one? The benefits are coming from the big companies, and citizens are paying, and the big companies are not interested in that we are producing our own energy and not paying them. This is the main reason in Spain, at least. The problem with renewable energy is that it's not constant. When you have, for example, a coal power station or nuclear power station, you're producing electricity continuously all the time. But wind and sun is not constant. It changes from day to day, from day to night, from winter to summer. Then to produce energy with this kind of system, we have to be able to store energy, which is a new concept, but it's not very well understood. We have to store energy. And there are many different systems to store energy. We can talk about mechanical, electrochemical, thermal, electrical, hydrogen, chemical, okay? And we are going to talk mainly about electrochemical system, which are batteries. We all know batteries because we all use batteries in our cell phones, laptops, etc. Different systems, for example, lithium-ion, flow batteries, supercaps, which is not electrochemical, it is similar. Okay. But before going to the electrochemical system, I want to introduce you a mechanical system, which is a pumped hydro. In Spain, for example, we have 5 gigawatts of this energy storage device, and it will give you one idea of how it works, energy storage. This is an image of what consists the energy storage. You need 2 reservoirs, 2 water reservoirs, and they are connected. Then when you have an excess of electricity in the grid, what you do is to pump the water from the lower reservoir to the upper one. Then you are using the electricity that is in excess in the grid to store the energy in form of gravitational energy. You are moving the water up to the lower to upper level, and then when you need electricity, when you need to produce more electricity, what you do is to allow the water to go down to the lower reservoir, and through a turbine you produce electricity. Then you are able to store energy in this form. Okay, this is a mechanical form. You are moving water up and down, up and down. And I like to show this example. This is El Hierro. This is a very small island in the Atlantic Ocean, Spanish island, very small, 11,000 people living there. And they are consuming around 11 megawatts of energy, of power. And they were using mainly diesel. The diesel was transported by ship, and they have a thermal station to burn the diesel and to produce energy. But it was 5 years ago, they started with this system. They installed only 5 windmills, only 5, 2 megawatts each, and an energy storage device like this, the hydropower station. And with this, they have been able, in just 1 year, to reduce 60% the consumption of diesel. Okay, that's a very important case, and I think it's relevant in a country like Greece with so many islands, small populations, and it's quite simple. Only 5 windmills, 2 megawatts each, and 2 water reservoirs, and they are reducing the consumption of diesel 60% the first year, which is a very, very important amount. Okay.
Ricardo,
Yes.
I'm sorry for interruption. I cannot see your screen myself. Can you stop share and share it again?
Okay. Stop, dejar de compartir. And start again.
Okay, you make it full screen. Thank you.
Okay, can you say now? Perfect. Okay, then when we are talking about energy storage, we have to talk about quite different things at different levels. For example, different scales, different solutions. For example, in stationary applications, You can think in your house, you have a house, you install some photovoltaic cells, and you are able to produce your energy. But maybe when you are at home, during the day, you can use this energy, but if you are at your office working, you cannot use this energy, and you need this energy at night. Then you can install a battery energy storage system to store the energy you are producing during the sunny hours, and you can use at night. Okay, that's so simple. I think these systems you can buy in IKEA. It's becoming popular and becoming cheaper anytime. That's a solution for a small battery, but we need solutions also. We need solutions also for large storage, large scale storage. For example, for isolated grids, you think in one island, for example, or for the national grid, then you don't need small batteries, you need large batteries working in the megawatt or hours scale, okay? And that the different solutions for different applications. The Department of Energy of the United States have some objectives. They want to reduce 90% the cost of this system, of these batteries, in 10 years' time, which is very ambitious. I don't know if we will be able to get there, but it's important to reduce the cost of these systems to get them into the market. And that's talking about the stationary applications, but we have to talk about mobility. Mobility is also very important in energy storage. Talking about mobility, we can think about electronic devices, which are, I think we have this solved. We have lithium-ion batteries we can use in our cell phones, in our laptops, etc. But thinking about mobility, we have to think about vehicles. We are thinking about the electric vehicle that running with batteries, okay? These batteries should be around 200, 300 kilowatts per hour of energy. And the problem with these batteries, they exist. They have more and more electric vehicles running in our streets. If you go to Norway, they are the most sold car is electric. If you go to Spain, they are very rare. Maybe in Greece also. And the main reason is that they are still very expensive, okay? Rich countries can run with these kind of vehicles, but countries from the south is not that easy. And again, the Department of Energy of the United States want to reduce the cost of the batteries, this kind of batteries, nearly by half for the next years. We will see. But also the problem with the batteries is how long they last. We are used that in our cell phones, for example, the battery is lasting a couple of days, the first when we buy the new cell phone. But after 1 year of use, the capacity of the battery is seriously reduced. And after 2 or 3 years, we have to change our cell phone or change the battery at least. But we cannot change our car every 2 or 3 years, okay? They have to last for many years. And about mobility, thinking about cars, but we have to think also about marine transportation, and we have to be thinking also about air transportation, which are producing a lot of CO2. Here you have one example of an electric vehicle, electric vessel from China. It's a Yangtze River Three Gorges 1. It has a battery of 7.5 megawatts and able to run 100 kilometers with a single charge, which is a number. Again, in Greece, you have ferries moving from one side to the other. This is a cruise, lightweight. I don't think we are ready to think in large vessels moving a huge amount of materials, very heavy. Maybe we have to change again our mind and think maybe we don't need to transport so many things. We should be producing in our countries instead of importing everything from China. Then we have to change our mind a little bit. But again, that will be in the future. I don't know how far we will be able to get, but the small boats are able to be fully electric. In countries like Holland and Amsterdam, for example, all the transportation in the channels will be electric soon. and that will be easier, but large vessels are more difficult. And if we think about air transport, it's becoming even more complicated. We will see in the future some electric aircrafts, but I don't know what year. I don't know if I will see these aircraft running. Okay, then go to the next part is the carbon. We want, in this presentation, I want to talk about carbon atom, carbon material, sorry. And I want you to explain why can use carbon materials for these applications. Carbon materials are not very popular. Many people know metals, aluminum, steel, copper, many metals. You may know plastics, but if I ask you about different carbon materials, what are they used for? Many of you will not know many, maybe rackets and this kind of materials made of carbon fibers. I will try to explain why we use carbon materials in these applications and many other applications. We have two popular kind of carbons, which are diamond and graphite. We studied them at the school as an example of allotropes. Diamond and graphite are made of pure carbon. They have the same chemical composition, but we know they have quite different properties and quite different price, you know? And everything is related how the carbon atoms are distributed in the space, how they join each other. We have sp3 hybridization for diamond, sp2 for graphite. There are other materials with different hybridization. We will see now. But when we are talking about carbon materials, we are talking about the graphite family. And I want you to keep in mind, well, how is graphite? Graphite is made of layers of carbon, pure carbon, stick one over the other, and you have interspace between one layer and the other, okay? Keep this image in mind. I will give you some very quick idea of where carbon materials are used in the actual industry and in the actual market. All the steel that is produced in the world is use carbon materials in their production, both in the blast furnace and the electrode and the electric arc furnace to recover steel. They use different kind of carbon materials. In the blast furnace, they use metallurgical coke, which is carbon, and in the electric arc furnace, they use graphite electrodes, large size graphite electrodes, different carbon materials. All the aluminum produced in the world uses carbon in the production. Again, carbon electrodes that are consumed during the aluminum production. For every 3 kilograms of aluminum produced, you consume 1 kilogram of carbon. And in this case, this carbon electrode is made of petroleum coke and coal tar pitch. Elastomers production, you see all the wheels are black in our vehicles, and they are black because they contain a large amount of carbon. In this case is carbon black, different type of carbon. And these carbon blacks are also used as plastic additive, inks, paints additive, toner for printers. Everything that is black in this market is because it has carbon materials. Very important, it's an adsorbent production in many industries. For water purification, pollutant removal, etc. They use activated carbon, totally different kind of carbon. Sport material, this is more known. Many people have rackets made of carbon fibers. And carbon is increasing the use also in aeronautics. This is nearly 50% of the weight of a plane is now made of carbon. You see all these parts that has color are made of carbon. Again, similar kind of carbon to the sport material, carbon fibers. And in aerospatial components, you see the space shuttle. Everything that is black in here is made of carbon. As again, carbon fibers, but a different kind. Carbon fibers, reinforced materials, carbon-carbon composites. Then there are many applications where carbon are used, and I want you to understand the reasons. In 2 or 3 minutes, I will try to explain you the reasons. We start from graphite. From graphite, we can have very sophisticated materials. The nanoscience, the nanotechnology was born with fullerene that was discovered in 1985. It's pure carbon, again, like diamond, like graphite, but it's a molecule with only 60 atoms of carbon. And you have carbon nanotubes were later discovered in 1991, I think, and graphene 2004. Graphene is just a layer of graphite. If you are able to isolate a single layer of graphite, you have a graphene. If you roll the graphene, you have carbon nanotube, okay? Then all these materials are related with graphene, with graphite, and there are more traditional materials like petroleum coke, carbon fibers, activated carbon that has been used for more than a century in many applications, as I showed you before. The reason depends on the different levels of order of the carbon atoms. And we saw that in graphite and diamond, everything is related with the position of the atoms. Again, within the family of the graphite, everything depends on how they are disposed in the space. You have pure crystalline graphite, the highly oriented periodic graphite. You can see that's an image of the atomic form microscope. You have the carbon atoms. You can see one by one, perfectly ordered in the space. This is a very crystalline material. But if you go to the other border, to the classic carbon, you can see the layers. You can see by high resolution transmission electron microscopy, you can see the layers, but they are not perfectly aligned. They are twisted. They have many defects. You have only 4 or 5 layers on top of the other, or just one or just two. You have the same layers, but highly distorted. And this is the reason you have different materials. That depends on how crystalline the material is. You can have here one image, easy to remember. These cannelloni are more or less like graphite. You have layers of them, very well ordered. And if you distort it a little bit, the layers, and you break down the layers to small pieces, what you have is activated carbons, glassy carbons, different kind of materials, okay? And then everything is resumed here in this picture. You have high crystalline materials or low crystallinity materials with different properties and therefore with different applications. High crystallinity materials have high electrical conductivity, high thermal conductivity. Low crystallinity materials, high surface areas, etc. You can see here the different properties, and everything depends on the structure. Okay, you can transform one material in the other. Some materials with low order, when they are treated at very high temperatures, 200, nearly 3,000 degrees centigrade, they transform into graphite, and you can break down the graphite by a strong chemical attack. For example, this is what we do to produce graphene oxide. You can disorder the material by a chemical attack. Okay, and that's everything you have to understand. Depending on the structural order, you have one material or the other, and you have different properties and therefore different applications. And these applications I'm marking here in red are relevant for electrodes, for applications and energy storage. The electrical conductivity is very important. Chemical reactivity, in some cases we need high reactivity, in some cases we need inertness, and in some cases we need high surface area, in other cases we need low surface area. Go to the electrochemical part. First of all, I want to introduce you what is a battery, very general concept of a battery for you to understand. A battery has 2 electrodes, positive and negative one, made of different materials. These 2 electrodes are immersed in an electrolyte, separated by a membrane, and you have an external circuit connecting them that allow the flow of electrons, okay? This is the way we can charge and discharge our battery, connecting through an external circuit. This is very similar, and this is the reason I show you this energy storage system, the hydro pumped, because in somehow they remember a battery. You have the 2 water reservoirs play the role of the electrodes. Okay, you have 2 electrodes in this case, But instead of having gravitational energy, potential energy, what you have is electrochemical energy between the two different electrodes. In this case, you have gravitational energy, mechanical elements. But in the electrochemical battery, you have different electrochemical potential energy. When you open the tap that connected two reservoirs, the water flows down. It's the same when you connect your two electrodes, the electrons spontaneously flow in one direction, and you can make them flow in the other direction, forcing, just applying energy. This is what you do when you charge and discharge your battery, okay? Then, to have a battery, you need two materials that are capable to give reversible redox reaction with the maximum potential energy. You have to be able to charge and discharge for many times, as much as possible, and you need to do it very fast. Okay, that means to have power. But there are other important parameters we have to define when we make a battery. Is the cost of the material, which is very relevant. Environmental issues, which are very, very relevant. In the history of batteries, we have been using lead, we have been using mercury, we have been using cadmium. The most toxic heavy metals we have in the world have been used in the batteries, still used in the batteries, especially lead. Then we are looking for new materials we are not so harmful for the environment and for us. Safety is a very relevant issue. And for example, in lithium-ion batteries, it's not fully resolved, safety, efficiency, and for some applications, mainly for mobility, energy density and power density. How much energy, how much power can you put per kilogram of material or per liter, per volume of material? In a car, you have a very limited space to put your battery, then energy density is very important. And in here you have the history of batteries. Why we are moving from the former lead acid batteries to lithium-ion batteries? Because you have more specific energy and more specific power. Lithium-ion batteries and lithium metal batteries are the ones that offer us higher energy and power density, and this is the reasons that the one we are going to use in electric mobility. Okay. The reason is the electrochemical potential. Lithium, if you have a table of the electrochemical potential of all the materials that you have in the periodic table of all the elements, lithium has the more negative potential, and that allows you to get more energy in very limited. In one cell, you have 3.7 volts. If you go to nickel metal hydrides, you need 3 cells put together to have the same voltage. Okay. With the difference that lithium is a very light metal, has a very low atomic weight. In here, you're using heavy metals, nickel and metal hydrides, some other metals. That makes you have more weight and less energy. Okay. And the key point in batteries is lithium-ion batteries, the one we are using all the time. And I want to show you the scheme of a lithium-ion battery and how it works. This is the scheme. The materials we use in the cathodic material is normally lithium metal oxide. The most common one is lithium cobalt oxide. Cobalt is expensive, difficult to obtain. Trying to move to lithium manganese oxide. Can use other materials. Lithium iron phosphate, for example, are also commercial. But you need, anyhow, one material that is able to keep lithium in the structure. And in the negative electrode, what you have is carbon material. You have graphite as the anode material in all lithium-ion batteries that you find in the market. That's a huge amount of graphite is used for this application. And the reason, if you remember the structure of the graphite, this layer structure, between the layers, you can introduce the small lithium atom, okay? Then you have an electrolyte, which is relevant, but not for this talk. And here you can see how the lithium battery is charging and discharging what people is calling the rocking chair battery. You are charging and discharging, charging and discharging your battery. And the lithium is moving from one side, is from the cathode to the anode. You have intercalation of lithium in the cathode and in the anode. You have chemical reactions occurring. The lithium is not intercalating by itself. You need some chemical reactions to occur. You always have chemical reactions in any kind of battery. In here, for example, cobalt in the positive one is oxidizing, reducing between cobalt +2, cobalt +3. When you have the oxidation and reduction, the lithium goes out of the structure of the crystal and goes into the anode, is reduced to lithium 0, to metallic lithium, and go into the structure. Okay. Then you have chemical reactions, and you see when lithium goes in and out of the structure of the positive and negative electrode, you are changing the physical structure of the material. You have some kind of expansion, contraction, and this is very important for the long-term properties of the materials. Okay, now you understand why we have graphite in lithium-ion battery. We are going to change to quite different system. It's called supercapacitor. It's not so popular. There is a market for supercapacitor, but it's not a huge market like in the lithium-ion batteries. The main properties of supercapacitors is high power, low energy, and very high cyclability. We are talking about 1 million times charge and discharge. In a lithium-ion battery, to compare, we are talking about 1,000. Only 1,000. 1.5 thousand, no more than that. But in supercaps, you are having nearly 1 million charge and discharge. And I will try to explain you the reasons. Supercaps, as I told you, are characterized by high power and low energy. And I will explain you again the reasons. What kind of materials are used in the supercaps? There are 3 options. You can use transition metal oxides, conducting polymers, or carbon materials. Conducting polymers have not reached the commercial scale because they last very short cycles of charge and discharge. Transition metal oxides, yes, they are commercial, but only for military applications. They're made of ruthenium oxide mainly, very expensive, and only in military applications. Therefore, 95% of all the supercapacitors that are in the market are based on carbon materials, not in one electrode, but in both of them. Positive and negative electrodes of supercaps are made of carbon materials, but not graphite, a different one. I will explain you how it works. Before going to supercap, let's remember what is a capacitor. If for having a supercapacitor, remember what is a parallel plate capacitor. Is the one we study at the schools. We have 2 aluminum foils, for example, separated by a dielectric. The capacity, the amount of energy you are able to store, depends on the surface of the aluminum plates, depends on A, and the distance. That's D. Okay, we have to keep this equation in mind. Capacitance depends proportionally, that's the permittivity of the dielectric, proportionally to the surface area of the electrodes and the distance between the electrodes. Moving from a capacitor to a supercapacitor, the first step is changing the dielectric for one electrolyte. Think, for example, in a water solution of sodium chloride. You have ions, sodium, positive ion, chloride, or negative ion. When the supercapacitor is discharged, what you have is the ions randomly distributed in the electrochemical cell. But when you charge, what you have in the negative electrode is attracting the positive ions, in this case sodium. And the positive electrode is attracting the negative ions, forming what is called the double layer. This is the image when it's charged and discharged. And the mechanism is totally different from a battery. You have no chemical reactions. It's just pure electrostatic separation. This is the reason that the processes are very fast And this is the reason for the high cyclability. You can charge and discharge 1 million times and nothing happens. You are not modifying the chemical structure of the electrodes. Remember, in lithium-ion batteries, you are changing the structure when lithium goes into the material. This is a phenomenon that only occurs on the surface of the electrodes, okay? And this is what we call the double layer. Let's think a bit more about this. Why we change from a capacitor to a supercapacitor? The first point you can see in this graph is D. The distance in a capacitor was the distance between the two aluminum plates, which is in the millimeter scale, more or less. But now the distance is represented between the distance between the electrode, one of the aluminum plates, and the charges, the positive charges or the negative charges stored on the surface of the electrode. Now this distance D is in the molecular range. We are moving to nanometers, no millimeters, and we are increasing several orders of magnitude the capacity. Okay, and the second, a bit more complex, is A. A represents not anymore the surface of the plate, aluminum plate, but represents the contact area between the solid electrode, the aluminum, and the liquid electrolyte. If you have, for example, 1 square centimeter of aluminum, the surface area in contact with the electrolyte is 1 square centimeter. Nothing special about it. But what does it happen if you put a little amount of carbon, activated carbon, on top of the aluminum? If you put the same amount, I put one example, just putting 2 milligrams, 3 milligrams of activated carbon, standard activated carbon, the surface area is now 4,000 square centimeters. That's if the electrolyte goes into the porosity of the carbon, what you have increased the A, the surface area, by 3 orders of magnitude. Then the changes in this A and D is what transform conventional capacitor into a supercapacitor, increasing the capacitance from microfarads to thousands of farads, okay? Increasing several orders of magnitude. Just going back to this concept, what you make is to transform the electrode not in a smooth surface, but using an activated carbon, what you have is a high surface area, and then the ions are absorbing between all this surface area, increasing A. Different materials are having, different carbon materials are used, mainly activated carbon. Activated carbon is the most important because they are very cheap. But in research, we have been working with carbon nanotubes, graphenes, activated carbon fibers, carbon templates, many different materials, different electrolytes, different problems with resistance. What are supercapacitors useful for? What are the main applications in the future for supercaps? It's what is called regenerative braking. You have an electric vehicle using a battery for propulsion. Batteries have energy, but they have no power. They have limited power. Then if you can use the energy of the battery and the power of the supercapacitor, you have several advantages, mainly fuel saving in city driving. When you are driving in a city, you are driving in the mode go and stop, go and stop, go and stop. Every time you go, you have to put energy in your vehicle. And when you stop with conventional brake, we're transforming your kinetic energy into heat, losing all the energy. But if you have a supercap, you can transform this kinetic energy into electricity and charge your supercapacitor. And your supercapacitor is helping you when you start to move in the car. This braking and accelerating occurs in a very short time, and then you need power, and your battery has no power, okay? Then you can save something like 40% of energy. One more example, coming back to China, they have this electric vehicle, 2020, with a supercaps. It can be charged in only 30 seconds, and is able to save 85% of braking energy. Okay, you recover 85% of the energy that you have in your vehicle, which is a very important amount. These vehicles are very special. China has this technology, and they have the money, and they have the ability to make these demonstrations. But this is very important because you can charge in only 30 seconds. The time you are stopping to get people in and out, you can fully charge your vehicle and go to the next stop. Okay. And now we go to the last example, very short example. Redox flow batteries. You see the scheme of a redox flow battery, you see that it's more complex. You don't have only the battery, the electrochemical part with the positive and negative electrodes, with electrolytes. What you have is two tanks outside of the system. Okay. We have two electrodes, positive and negative, like any battery. But in this case, we have two electrolytes, not only one. And the electrolytes are kept outside of the cell, not inside. We have a membrane, and the energy, the big difference in this kind of batteries, is that the energy is stored outside of the battery. It's stored in the tanks. Then these tanks, you have the electrolytes, and they are pumped within the cell separately, the positive and the anolyte and the catholyte, the positive and negative electrolytes. You have involved chemical reactions. For example, you have the reactions here with vanadium salts. In the negative electrolyte, you use this reaction, vanadium 3, vanadium plus 2, oxidizing and reducing. In the positive electrolyte, you have vanadium 4, vanadium 5, oxidizing and reducing. Okay, two different systems with the potentials, etc. What's a good point of this battery? The benefits. The electrodes are inert. That's I don't like this word very much. It doesn't mean, it means that they are not modified. The chemical reactions occurs on the surface of the electrodes. You have vanadium oxidation and reduction in the surface, on the surface of the electrodes, but the electrode itself is not modified. That means long cycle life. This battery, lithium-ion battery, lasts 1,000 charge cycles. In here, we are talking about 10,000 cycles, okay? And the most important property of this system is that they have independent values of power and energy. The energy is in the electrolytes. If you want more energy, what you need is put more electrolyte, larger tanks. Then you can store 1 megawatt, 100 megawatts of energy, depending on the size of the electrolytes. While power depends only on the electrochemical cell, on the electrodes, how fast the electrodes are having the reactions. These batteries have some drawbacks. You have electrolytes moving, that reduces the efficiency of the cell. Lithium-ion batteries get easily 95% of energy efficiency. In this case, you are moving around 70-75, which is not that good. And the point in here is what kind of electrodes we are using. And the answer is this. The electrodes that we use in this kind of batteries are carbon fiber felts. Something like this. It's commercial material. This is the carbon fiber felt seen by scanning electron microscope. This special structure allows you to go through the electrolyte, to go through the electrode. And what we have to do is to modify the carbon surface to have fast kinetics on the chemical reactions, okay? Just one example, we have been involved in our group in one important project. It was around 4 million euros to build a 50 kilowatts battery. You have here, in our group, we have been making 1,200 electrodes, large size electrodes, so what keep us busy for a while, to make this kind of battery. You see, this is it's not a conventional battery. You have the electrolyte tanks, you have the stacks of the electrodes, you have the electrochemical part in here, and the electrolytes are independent. That's a different concept, difficult to understand. But in here, just to finalize, you have the scheme of why different electrochemical systems have different carbon materials as electrodes. Lithium-ion batteries, we have seen we are using graphite because of the structure of the graphite, and we are working with intercalation of lithium inside the structure of the graphite. In supercapacitors, we use activated carbons because of the high surface area, and that gives us high power, very high cyclability. And in the redox flow battery, it's a very good system for large-scale storage. We can easily move to megawatts per hour of energy stored. And everything is a question of surface chemistry. We want carbon fibers, we modify the surface for have very fast chemical reactions, okay? Then we use different carbon materials for different kind of electrochemical systems, and that's everything. Thank you for your attention. And this is my group in Spain. It's nice people. We have some staff, doctors, postdocs, we have technicians and some students doing their PhDs. And if you want to ask me something, thank you for your attention and for your patience.
Thank you, Ricardo. Please stop sharing the screen in order to start the discussion. We have few moments for few questions. I mean, if you have any questions, please raise your hand, your virtual hand, or write your question in the chat. In different case, I will start the questions. Ricardo, I have some questions mainly from. So my first question is like, you mentioned an impressive figure, how fast or relative faster than Greece. You made this transition from the carbon-based fuels to renewable energy sources, energy fuels in Spain. So I would like to ask you, what were the first challenges for this transition? I mean, I suspect that it was not such an easy transition. Apart of, let's say, the different companies, how can I say, like strategies that they lost, you know, the priority. What kind of other challenges, like from the society, from the financial point of view, did you face in Spain? This is my first question.
Yeah, initially, this transition started with a government that put a lot of money, public money, to make the transition. And there was a lot of people complaining, we are paying special taxes to get this clean energy. And we don't trust this, we don't trust in this clean energy. This clean energy is not enough. It's not going to give energy enough. We will always rely, we're talking about 20 years back, we will always rely on coal or oil. But at that time, this technology was more expensive than traditional technologies, coal. Then we need a lot of public investment. And I think the government was right. We make this transition. A lot of criticisms coming from different sectors, political sectors. But now these technologies are cheaper.
Mm-hmm.
This is the right point we made. But in my point of view, this is more political than technical, is that in Spain, the energy powers and energy companies are very powerful, very powerful. They have a lot of influence in the government. And then we do a lot of work in wind energy, because the electric energy companies are using these windmills. Windmills are very expensive, and the electrical companies are getting the public money, but we didn't invest in photovoltaics. You see, the government in Germany give money to people to put solar roofs, but they give money to people. In Spain, the government give money to the large companies. Then there is no reason for Germany having 1.4 million solar roofs, while in Spain, which we have more sun, much more sun than in Germany, we have no solar roofs. For example, when the first time I came to Greece, I see that in your roofs, you have system to heat the water with sun all around Greece. You don't see this in Spain, which is unbelievable because we have the sun.
Mhm. So you believe that this is a political decision?
Yes, I really believe that, yes.
Okay.
And when President Obama came to Spain 15 years ago, we were a model for the United States in the energy transition. 2 years later, a new government make a law that forced people to pay a tax to use the sun, which is absolutely crazy, you know? If you want to put a solar roof, you have to pay a special tax to use free energy like the sun. That is absolutely crazy. And that goes to our country, 100,000 unemployed people. We have all this new technology coming up with many small companies, and they close, all of them close down. But it was something to understand, but politicians have something.
Thank you. Before I will move to my second question, I will have a question in the chat from Professor Kakavelakis. Thanks for the nice presentation. Could you please comment on the source of the graphite, natural or synthetic, used in state-of-the-art batteries and supercapacitors? Which one of them have lower environmental impact? Thank you.
Graphite is becoming now a critical material. You know, natural graphite resources are limited, and synthetic graphite is mainly coming from petroleum sources. Then, which one has less impact? I would say natural graphite. Natural graphite is more crystalline, is better as far as it's clean. In natural graphite coming from a mine, you have ash, different metals, different oxides, different components that you don't want to have in an electrochemical device. Then you have to clean this material. But there is a big concern on where the graphite is coming from. Yes, this is an important question, especially for the future. In the future market, lithium-ion batteries are going to grow and to grow and to grow. And we are thinking, where is the lithium coming from? There is no lithium. Well, there is lithium in the planet. And now we are mining lithium from South America, mainly Chile, Argentina, in the big high altitude salars. They have a lot of lithium, and they are exploiting lithium in there. There is lithium in the sea, but it's more difficult to get, more expensive. And the same problem we have with lithium, we have with the graphite. What has less impact? When we are talking about energy, we have to change our mind how much energy we are consuming. We have to stop. We cannot only think how to produce energy, moving from, we have to give up fossil fuels and go to renewable, but we have to reduce the use of energy. And we have to be much more efficient in the use of energy, which is quite a different concept. I said before on transportation, okay, we'll be able to transport these huge vessels by electric power. I don't think so, but maybe we don't need to transport all these materials. Just a deep change in our society, what we need in the future.
Thank you, Ricardo. There is another question from our colleague Bara. If I have pronounced well your name, I'm sorry if I have done a mistake. It's a nice presentation. Thank you. For the redox flow batteries, you use modified carbon fiber. Do you modify it in your group? If yes, how do you do that?
Yes, we did the modification in our group. For the small scale, we, for example, in the negative electrode, you have carbon fibers are any carbon material, mainly is hydrophobos. Then the electrolytes we're using are water-based. Then we have to improve hydrophilicity. Then oxidizing the carbon fibers a little bit, just the surface, very light oxidation helps a lot in the improvement of the performance of the batteries. And one of the main concerns in the lithium-ion, in the redox flow batteries, is the negative electrode. When you have vanadium 2, vanadium 3 oxidation reduction, competing with a secondary reaction, which is hydrogen evolution. The electrolyte is a sulfuric acid solution with the vanadium salt in sulfuric acid solution, high concentration of hydrogen. Then if you go to negative potentials and we have to go to negative potential to have oxidation reduction of vanadium, you compete with hydrogen evolution. Then you have to be able to inhibit this reaction. And for example, we did modifying with nanoparticles of bismuth. We put some bismuth nanoparticles, that for a small scale. For the large scale, for the 1000 electrodes, we only oxidize, we design a special furnace for a smooth oxidation of the surface to improve hydrophilicity.
Thank you. And my last question, and I think we should stop here, is the following. It seems, following your presentation, that the layer materials are something very attractive regarding the technologies that you are using, because you are creating the space for the lithium ions,
Yes.
To insert. So
Yes.
what are the criteria? Which kind of 2D materials? Because there is a compensation here. Like how many layers you are going to use in order, then to compensate the conductivity, because these are used for electrodes, if I got it well. So how do you select? Why only graphite? Because you will then probably it's low cost, but what about the potential of the other 2D materials in these applications?
Yeah, graphite, because of they have several advantages. Cost, becoming more expensive, and the use is increased. Cost, low reactivity, because when you are working in this negative electrode, you are at very negative potential. In lithium-ion batteries, you are going to -3, nearly to -3, 3.5 potential. Then to have very low inertness, very low surface area like graphite has, and inertness, yes, it's very inert, not to have secondary reaction with electrolyte. And to have electrical conductivity, not many materials combine all these properties. Important about the layered materials, we are talking about lithium, but we would prefer to use sodium, much more expensive, much cheaper, more common, but larger. Then we are looking for new materials that are capable to introduce lithium, not lithium, sodium or potassium. A lot of work has been done on sodium batteries, sodium-ion batteries, but we need to find the right material to intercalate, not lithium, but sodium, to have a reversible intercalation, the intercalation process with sodium.
And what are the KPIs in order, to select them? The distance of the layers. What are the criteria? The inertness with sodium. What is like? I don't know. That's why I'm asking.
The inertness with sodium. The problem with sodium is the size. Sodium
Size.
Okay. It doesn't fit into the layer. You have a different layer spacing to fit sodium. And graphite is not good enough. And trying to develop new materials or to do something to increase the size in graphite, which is not easy.
Thank you very much, Ricardo. Muchas gracias. And also, Dimitra, for the introduction, and, for the honor to be in our university. Always we would like to attract for teaching, for research, scientists from abroad. It's a part of internationalization as well. So, Dimitra, thank you as well for introducing us, Ricardo. All the best for your collaboration. And for the students that have participated here, you can see that the world is open, so many laboratories. One thing that you are missing, Ricardo, is a Greek from your laboratory, from your group. And all the best, and thank you very much. We will continue next week with another Athena talk that it will be announced through our network. Thank you, all of you, for the participation, and the video will be uploaded, and you will be informed within the day. Thank you.
Thanks a lot.
Bye.
Thank you, Ricardo.
Thanks, Dimitra.